Okay, I think we're back. Thank you. I can do it without slides, but for the demos, it's difficult. I can mime, deep learning training, but not that exciting, I guess. Okay, welcome back. I hope you had a good lunch and coffee, right? Because you'll need it. In the previous session, we talked about the theory, the concepts of deep learning and how the training process works and all the magic that happens under the hood. So in this session, we're going to take all that stuff for granted now, and we're going to start training and running models. And to do this, I'm going to use a deep learning library called Apache MXNet, which is the library of choice for AWS when it comes to deep learning, and of course I will explain why. And most of the session will actually be running demos and seeing those concepts that we saw earlier in action, right? So we're going to try and apply everything that we learned and run some code. Okay, and yes, and of course I'll share some resources, so more resources for you to learn. I think I need to change my batteries here. Okay, let's get started with Apache MXNet. So MXNet is an open source project. It started in 2015. And originally was a university-driven project. Carnegie Mellon, and then University of Washington joined. And as the project grew, of course, then individual developers and companies came and contributed. Not sure how accurate that stat is, but probably a few months ago, the top committer at MXNet was still an Apple engineer, and AWS had 4 of the top 10 committers. Okay, and so why do we like it? Well, the first reason is it supports multiple languages. If you're already doing deep learning today, most of the existing libraries usually work in a single language, right? Or maybe 2. But most of the time, it's going to be Python, C++, but mostly Python, right? So you have the choice between Python and Python. Yeah, that's a choice. That's a choice. And I love Python, so personally, I see nothing wrong with that. But as it happens, we have millions of customers, and well, we could run a poll right now, and some of you are using Python, some of you are using Scala, some of you are using C++, etc., etc., and maybe some other less respectable things as well. No names, right? But that's okay. So my point is, more languages are just better, okay? So if you work with MXNet, you can do Python, of course. You can do R, which is a very popular language for data science. You can use MATLAB. Actually, you can import MATLAB models into, you can import MXNet models into MATLAB. You could use C++, of course, because MXNet is natively written in C++, so that's obviously the fastest option there. You could use Scala if you wanted, and we also have an SDK for Spark, right? We want to make sure to mention it. So if you want to run Scala APIs on MXNet, that works. And what else? What did I forget? Oh yes, and Perl. All right. Anybody want to do deep learning in Perl? Okay, here's the door. I don't know. Somebody loved it enough to build the APIs, right? So, all right. See, it's a very open library. You can add even Perl to it. So that's good. Seriously, the reason why I think this is important is because when you work in the experimentation environment, you tend to like flexible languages like, let's say, Python and, it's an obsession, Python and R. But as you move into production and you tend to freeze the model, then you probably care more about performance, right? Speed, training speed, and of course prediction speed. And then I guess C++ and Scala will give you good results. So if your library only supports Python, well, then you have to live with Python in production. which is maybe not the fastest option, or you have to rewrite and retrain your model with different libraries supporting a different language, and that's a big no-no for me, right? It's a huge source of problems and time and wasting time. So having multiple languages is good. You can experiment in Python very easily, rewrite your code or you write MXNet code in C++ and use the same model that you trained in Python for prediction and have maximum performance. Okay. The second thing that we like is that MXNet works equally well in very tiny environments, Raspberry Pis, deep lengths that Adrian mentioned this morning. Small things, right? Small things are able to do prediction with MXNet. And of course, as you move into bigger things, high performance servers, multi-GPU servers, even maybe running training on multiple instances, distributed training, etc. MXNet scales very, very well. And we benchmarked it to up to 256 GPUs. So that's an expensive demo, expensive benchmark, I think. And we showed that MXNet scales linearly up to there. So that means if you have a huge training job and you need to run it on one GPU for, let's say, 16 days, well, if you run it on 16 GPUs, it would take close to a day. Okay, that's what linear scaling is. So very good. And we don't necessarily see these features in other libraries. And well, the last thing we like very much is that it's now part of the Apache incubator. So it's really Apache MXNet. And that means no single entity controls the project. No single entity could decide to steer the project in a direction that the community doesn't like. And no single entity could decide to close some part of the source base, of the code base. And unfortunately, these things have been known to happen in the past. Okay, so these are the main reasons why we like it. So what will you find in MXNet? You'll find, so in this case, the Python API. It's a high-level API. The objects that you work with are very high-level objects. Usually they're full layers. Okay, so you can recognize that first one, fully connected. It's basically one layer for a fully connected network, just like the one we saw in my previous talk. We see the convolution object. Again, that lets you define a convolutional layer. And the pooling object, which I mentioned too, LSTMs, etc., and more. So you don't get to work with every individual neuron, which 99.9% of us don't want to do anyway. You just combine layers and activation functions in just a few lines of code. And using this Lego box, right, you can build all of those use cases that I told you about this morning. Remember the GitHub projects that I showed you? They go from image recognition to OCR to machine translation, etc. So my point is MXNet is flexible enough to build all those different architectures. Okay? A couple of newer features that I want to point out. I think they make a difference as well. So the first one is called the model server. And this is an additional tool present in MXNet. And as you guessed from the name, this will let you serve predictions with an existing web server that's built in there from any model that you train. Okay, so you can train your model in MXNet and just fire up the model server with a CLI command and start serving HTTP predictions. So it's very convenient if you want to test. If you want to test your app, probably it's performing HTTP-based predictions. So you don't have to write a test app, and you don't have to worry with all the plumbing. You can just fire up the model server and start running predictions. Okay, you could even use this in production. Why not, right? If you do some load testing and scaling, it's probably strong enough to be used in production to serve predictions. And the other feature that I like is called ONNX, quite a complex acronym, which basically lets you import and export models between MXNet and other libraries. So this includes Caffe, the Facebook library. The Microsoft toolkit is part of this. And if I'm not mistaken, I think PyTorch is part of it as well. So a couple I'm missing. We'd love to have them on board, but sounds complicated. So anyway, this means you could see on GitHub a very cool project based on a Caffe model, let's say. And you could just grab this model and convert it and load it directly in MXNet. Okay, so this extends, of course, the number of projects that you could use directly, the number of models that you could use directly. Okay, so it's a, and of course it goes both ways, right? You can export model to other libraries too. So pretty excited to have that. Okay, let's look at a couple of APIs, important objects that we'll see all across our code. So it's important to be familiar with those. So as we saw this morning, the first thing that we do is we need, of course, to put our data into some kind of data structure that will be used for training, prediction, etc. Okay, so this object is called ND-array in MXNet, which is just a multi-dimensional array. Okay, so n-dimension array. Nothing more, nothing less. Okay, and as we'll see, this can be pretty big arrays. So that's where we'll load the samples, the labels, and this is what we'll train on. Then we need to build the models. Okay, we need to combine the layers, define weights, define activation functions, etc., etc. Okay, and we saw some examples of that API just on the slide 2 minutes ago. So the one that you saw actually on that slide is called the Symbolic API. Okay, it's the original MXNet API, which is very high level, and this works in symbolic mode. That's why it's called a Symbolic API. So let me explain. When you work in symbolic mode, you define the model, right? You combine the layers, you build it completely, right? And then it's frozen, and since it's frozen, you can optimize the hell out of it, right? It's like an execution graph, and you can apply graph optimization techniques to save memory, to save processing time, right? You can do all kinds of optimization on an execution graph. And you can do this because it's frozen, you know it's not going to change. And once you run this optimization, then you can train, okay? So this sounds really good, and it is, because it means you can get lower memory usage, you can get faster training performance, etc., etc. But the downside to this is that it's a black box. Okay, so once the training process starts, there's very little you can do, actually. There's very little you can do except wait. Wait for the training process to be complete and evaluate the results. So you can't stop the training process, you cannot inspect the layers, you cannot inspect the weights. And so if the training process goes wrong, it's very difficult to understand why. Okay, so this Symbolic API is very good when you need maximum performance. Okay, and that's probably when you're running prediction and when you know the network is performing. Okay, and when you're actually experimenting, when you're learning from the data, when you're trying to understand why, what network would be appropriate and why this specific network works and this one doesn't, well, then you probably should use the Gluon API, which is the newer API introduced last year. And this one is not symbolic, it's just what we call imperative programming, which is the way you and me write code every day, right? Just normal code. And so this means we can now stop the training process. We could have the Python debugger in there, and we could step through the training process. We could look at weights. We could inspect everything. Okay, so we could actually treat the training process just like every other piece of code. Okay, and that's what the Gluon API does. Now, the downside to it is, of course, you're not running all those fancy optimizations. So training with Gluon is going to be slower. Okay, and predicting with Gluon is going to be slower. Unless, because it's never that simple, of course, unless you use hybrid networks. Okay, so hybrid networks are a way to convert Gluon models into symbolic models. Okay, and then you get very, very close to the symbolic performance okay? But again, you lose the visibility inside the training process. So you get the best of both worlds, I think. You can use the Gluon API to build very flexible code that you could debug and inspect, etc. And then, if you're happy with that model, you could man, that's impossible to say. Hybridize it. Try saying that 10 times fast. Hybridize. Hybridize it and get really close to the symbolic performance, okay? Or you could just rewrite symbolic code and use symbolic code, okay? So, best of both worlds. Okay, the next object that we need is a way to serve data to the model during the training process batch by batch. Remember, we do batch training, and it would be painful to have to, yes? Sorry, you have to speak louder. I'm not sure I understand your question. So the Symbolic API, you'll see some examples, but the Symbolic API is just an API that lets you very easily build the networks, okay? But the difference between the Symbolic API and the Gluon API is that once the network is defined, right, once it's built with the Symbolic API, it's frozen, it's optimized, and you cannot inspect it during training. Okay, you just run the training and get your results, and if you like them, fine. If you don't like them, it's pretty difficult to understand why. Okay, that's the difference. The Gluon API is just code. So you can stop it, inspect it, debug it, right? It's different, okay? You can do the same thing. You can do the exact same thing with both, okay? You can manipulate the same objects, build the same models, etc. Again, the difference is one will let you inspect the training process, and one will not, right? That's the only difference, okay? Okay, so yes, the iterator. So the iterator will slice the data set automatically for you and let you serve those batches automatically. So one less thing to worry about. And of course, we need an API to start training and save models and load models, etc. And it's the module API. Okay, so we'll see those 4 or 5 things in the code. So all those notebooks that I'm going to use are on GitHub, and of course you will get those slides in the next few days, and so you will get the links as well. Okay, so let's get started. All right. So I should just stop this one for now. Okay. Okay, so here we go. Let me make sure it's stopped. Yeah, it's fine. Okay. Can you read okay? Yeah? Okay, if it's too small at some point, just let me know, okay? Okay, so let's start with a pretty simple one to put all those pieces together. I call it the hello world example. So what we're going to do here is we're going to build a synthetic data set, a random data set, and we're going to try and learn it, okay? Sounds like a strange idea, but maybe it's not so strange. Okay, so let's import MXNet first. And I'm going to generate 10,000 samples, okay? Each sample is just a vector with 100 random floating point values between 0 and 1. Okay, so my data set is 10,000 lines, 100 columns, and each element is just a random float between 0 and 1. Okay? And I will save 2,000 samples for validation. Okay? 80-20. All right, so just let's define some constants. Okay, and let's generate the data set. So that's done. Okay, so X is my data set. Okay, you can see the shape, 10,000 by 100. And I fill that with random values from a uniform distribution between 0 and 1. And then I generate my labels too. And my labels are random integers between 0 and 9 included. Okay, I've got 10 categories. Okay, so samples, 10,000 lines, 100 columns. Labels, 10,000 lines, obviously, and just one column, an integer between 0 and 9. Okay? Okay, so that's my set. So now I need to split it between training and validation. Okay, and I'm using MXNet APIs to do this. As you can see, mx.nd. I'm using the ND-array API here. And if you're familiar with NumPy in Python, this is very, very close to NumPy. Okay, if you'll be at home if you know NumPy. Okay, and I can see the different shapes. So I can see my training set here. Okay, 8,000 by 100 plus the labels, and the validation set 2,000 by 100 and the labels. Okay, so far so good. Now let's define a simple fully connected network. And this is actually the same as the one you saw this morning. So I've got an input layer called data. And one of the nice things about MXNet is I don't have to size it. Okay, I don't have to say how many neurons are in there. MXNet will figure it out automatically when I bind this to the data set. And then I've got a first fully connected layer with 1024 neurons, activated by the ReLU activation function that we saw this morning as well. And then I've got the output layer, okay, with 10 categories. Because remember, I've got 10 classes, so I do need to have 10 output neurons here. And I need to use a mathematical function called softmax, because if I don't do that, if I just keep this FC2 thing as my output, what I will actually get inside of those neurons will be arbitrary sized numerical values, okay? And I don't want that. Remember, I want probabilities, okay? So I just take those values and I run them through the softmax function, and what softmax does, so it's going to take those 10 values and it's going to transform them so that each of them is between 0 and 1, and their sum is 1. And then I can see those as probabilities, okay? And the last thing I'm doing here is I'm actually creating the model and saying I want to use a CPU to train, okay? That's another nice MXNet feature. If I wanted to train on GPU, I would just do this. And that's it. And that's all it takes, right? And if I wanted multiple GPUs, I would just have a dictionary saying MX GPU 0, MX GPU 1, etc., etc. Okay, so very, very simple to switch from one to the other. If you work on your laptop, probably you do not have a GPU, you can just work like this, and then move that code to the server and just change this and be happy. All right? Okay, then I need to build my iterator, so I'll just take my training set, my training labels, give the batch size, which I think is 16 here, and build that iterator, which will serve the data to the model, okay, so that I don't have to do it. Okay. And the last step before training is to do this. So I need to bind my iterators actually, to the model, okay? And then MXNet will actually resize or size the input layer according to the data shape, okay? So now my input layer will be 100 neurons because I've got 100 features. Then I need to initialize my parameters. Okay, because if you remember this morning, we said all those weights start from random values. So why should I even initialize them, right? I could start with the random stuff, okay? So probably, but as I like saying, not all random things are created equal. So there are some better random ways than others. And initializing those weights randomly, but in a clever fashion, will help you train better, right? So this is another one of these lose your sanity discussions, okay? So let's not go into that. Keep in mind, there are some clever initialization techniques that still use random data, but that lead to better training. And the Xavier method has been shown to work pretty well. And it's called Xavier because it's the first name of his inventor, Xavier Gouraud, another French researcher. Okay, you could use some other techniques, but this one works well. And the final thing we haven't discussed, of course, is we need to provide an optimization function. So we're going to use Grandpa SGD, which is fine here, and a learning rate of 0.1, which is a very typical value, right? and it's going to be fixed. So we're going to stick to 0.1 during all the training. Okay, and that's it, and now we can train. So how many lines of code did we actually write now? 3. Okay, this doesn't count. 4, 10. All right, 15, 20. Lots of constants, they don't really count. Okay, I'll give you 30 lines of code, right? Okay, so congratulations. You're doing deep learning in 30 lines of Python code that anyone can write, right? Anybody can read and understand this, okay? Of course, it's the first time you see this API, so it might look a little alien, but, right? How much time could you spend understanding all the finer details in this? Not too long, right? So this is it. This is why MXNet, I think, is a nice library, because you don't write a lot of code, and it's very high level, and it's very easy to understand. And you can focus on the model and the data, which is where the value lies, I think. So let's look at the log here. So we see the MXNet log. We see the epochs going by on the left here. Hopefully, we see the training accuracy going up. Okay, and we're training for 50, I think. All right, so fine, yeah, 53%, 57%. Let's keep going down. You know where this is going, right, if you were there this morning? Okay, here we go, 100%, right? So that's one thing I didn't lie about. Okay, we do get to 100%, which means, right, that this model can perfectly learn those 8,000 samples. So I could take any of those 8,000 random things, forward them through the model, and I would get the right category. Right? Alarm bells should be ringing. Okay, so of course there's nowhere else to go beyond 100%, so we stay there. Fine. What about validation accuracy now? Because remember, we don't really care about training accuracy. Well, we care about training accuracy going up, right? Because it shows we're learning. But what about other samples that this network hasn't seen? And you can actually guess what the value is going to be. All right, let's backtrack a bit. Let me have some coffee first. Why do we even use deep learning? What do we want to figure out with deep learning? We want to do feature extraction. So we want to find patterns, right? Okay, thank you. And then, yes, we want to be able to predict later on. Okay, but let's stay on the features for now, okay? What is this data set? Random. Should we find any patterns in there? Hopefully not. Because if we do, it means we have a really, really bad random number generator, right? Which is probably a security issue. All right, we're gonna break AWS with this demo. Okay, so we shouldn't find anything here, right? Okay, so we still managed to learn it because probably we're overfitting like hell, right? Now, if I take those random validation samples from 10 categories and they have no pattern whatsoever and my network has no clue whatsoever about any pattern because there isn't any pattern to be found, right? And you need to classify them in 10 categories. How often will you be right? 1 in 10. Yes. So what should be the validation accuracy there? %. Okay, so that's my not so silly example. You could fool a lot of people with this. Okay, that's a great one for interviews, by the way. I didn't say, right? This can fool a lot of people. Okay, because we learn many things here. We learn that garbage in, garbage out. Okay, it was true 30 years ago. It's still true with deep learning, okay? So once again, there is nothing magical about deep learning. If your data is crappy, if it doesn't have any patterns, if it's unclean, if it's full of missing values, blah, 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 you will not get good results, okay? So that's super, super important. If your data is meaningless, your model is meaningless too, okay? Now you understand how this works. Why would it be magical? Right? It's multiplications, addition, adding, and computing derivatives. It's just math, so it's not clever, right? It's just math. Okay, first thing we learn, we need to pay attention to data. Second thing we know now is training accuracy going up is very nice, but if we don't keep our eye on validation accuracy, we're just not looking at anything, right? We're just happy and then disappointed, right? Okay? And yeah, so these are the 2 or 3 things, I didn't count, that we need to keep an eye on, right? Quality of data, validation accuracy, and of course, testing with real-life samples. Okay? So, not so silly. Okay, now let's try and learn a real data set. So we're going to use one that I'm sure you've seen before because it's convenient and it's small. It's called the MXNet dataset. Of course, you've seen this. Right? It's handwritten digits. Oh, that's my blog post. Wow, I'm pretty high on Google. Cool. This is 50,000 handwritten digits, 0 to 9, and of course the game is to classify them properly. So since we're in Germany, I have to point out there's a better one if you're tired of working with MXNet. A small company called Zalando. Probably you've never heard of them, but I wish them a lot of success. Yeah? Do we have anyone from Zalando in the room? Before I make too much fun? No. They're a great AWS customer. Now, actually, it happened to me that I did a session somewhere else, and we had people actually working on this in the room, so it was pretty funny. So that's why I say hi to Zalando every time now. So they built Fashion MXNet, which is it's a drop-in replacement for MXNet. So it's got the same number of images, same number of classes, same image size. So it's completely identical, right? And you can just use this one as a drop-in replacement. And it's much harder to learn, of course, than the digits. So whenever you're happy when you get 99.7% accuracy on MXNet, and you feel you know everything about deep learning, move to this one and learn again, right? This one is giving me a harder time. But we'll stick to the easy one for today. Okay, so this data set, like I said, 50K images. Let me just clear this. 50K images, 10 categories, black and white images, 28 pixels by 28 pixels. So I downloaded it already, of course, a million times, so let's not do that again. We're going to train for 50 epochs. We're going to build an iterator. And this data set is so well known that most deep learning libraries actually have iterators directly for MXNet. So you don't even have to pass the file names. Very good. Okay, let's build another fully connected network. And this one, so it will have an input layer, of course. And well, we got a problem now. Because those are images, right? 28 by 28. So I don't count really well, but that's 2 dimensions. What did we see about those input layers for fully connected networks? They're pretty flat, aren't they? It's a vector. So we have to flatten that 28 image into a 784 vector. Fine? Okay. All right. That wasn't too bad. Thank you, MXNet, for the flatten operation. Then I have a fully connected layer with 1024 neurons activated by ReLU. Then I have a second fully connected layer with 512 neurons activated by ReLU. And then I've got my output layer with 10 neurons because I've got 10 categories because 0 to 9. And I use softmax again because I want probability or probability-looking numbers. Okay? See? 7 lines. And that's a pretty complicated model already, right? Okay? 7 lines of code. All right, let's run this. Click, click. And again, we need to bind it. And we're not going to use, we're going to use the GPU because I'm not paying my bills. All right, we're going to use the GPU now. Bind, initialize. And yeah, I'm not going to use SGD. I'm going to use one of those fancy adaptative optimizers. I'm going to use ADA Delta. Remember that those optimizers racing down the saddle point. This is one of them. And I'm going to start with 0.1 again. Train. See? Aren't you happy you came here today? Right? I guess some of you have been reading deep learning stuff for months. And it's like, man, I'll never learn this, right? Because it always starts with the big equations, right? This made me mad for 6 months, literally. And then I realized I could just ignore the equations and work with the code, right? And of course, at some point, the equations show up. Okay? When you dive deep enough, they do show up, and, well, it's up to you to decide if you want to learn them or not. But my point, and the only thing I want to convince you of today, is you can get a whole lot done without going into the equations, right? And you can actually be autonomous and build those models and use them in your apps without going into the science. So look at this. This is impressive, right? After one epoch, we get 93% training accuracy and 94% validation accuracy. Just one epoch. Okay, so this is learning very well. Okay, let's go down. Yeah, when we do it 100% again, so let's keep an eye on overfitting. Okay, 98.22. So hopefully this isn't going down. 98.23, 22. Okay, so it's kind of the plateau area now. Yeah, it stays stable there. Oh, and actually for the very last epoch, it goes up a bit. Okay, so 98.26. Not so bad. Let's save this model. That's all it takes. One API call. And now I have a local file with all the weights that I learned, and I can load this and share it and give it to people to use, etc., etc. Okay? Not really complicated. Okay, so 98.26. Is this good? Is this bad? Right, we don't really know. We don't really know, because that's what validation accuracy tells me, but again, what my users are going to send to this model are not those MNIST samples. They're going to send something else. They're going to send their own samples. So it's always good practice to test with extra samples that are completely out of the training set, of the validation set. Right? People usually call that the test set. So I said, well, I need a test set. So I took my favorite paintbrush application, right? Like a 5-year-old, and I drew some digits, okay? And I'm gonna take those digits, and of course they're 28 by 28, etc. And I'm gonna push them through the model and see what happens there. Okay, so I need a function to load an image. Okay, these are PNG images. So I just need to, I'm loading them with the OpenCV library. I'm normalizing the pixel values, because that's how the MNIST samples have been built. Okay, so pixel values are actually between 0 and 1. And then I need to make sure that the dimensions are in the right order, and I build an ND array. Okay, so I take a PNG image, and I build an ND array. Okay, predicting is quite simple. I just need to I take my ND array, and I forward it through the model using the forward API. Okay? And then I can read the outputs. Okay, so I will read the 10 probabilities on the output layer. Okay, and I will hopefully find that the top probability is the right class for this. Okay, not a lot of code. And then, of course, I need to load the model, which is as complicated as load checkpoint, right? We use save checkpoint to save it. And then I instantiate it, if you want. I bind it to my data shape. Okay, so this looks a bit weird, so let me explain. Here I'm going to predict one sample at a time, okay? One image, and then another one, and then another one, okay? So that's first one here says that. It's the batch size, actually. So this says I'm using batches of 1. I could predict 16 images at a time if I wanted, but here I just want to predict 1. Okay, so it's one image with one channel, because this is the black and white image. So if it was a color image, it would be red, green, blue. So we'd have 3, that's 4, 3 images. Okay, so one image with one channel, 28 by 28 pixels. Okay, so you have to get used to those shapes. It's not just 28 by 28. You'd be, okay, the shape is 28 by 28. Well, no. Right. When you work like this, you have to give the batch size and the number of channels. And then I'm done, right? So now I need to load the model that I trained. And I need to run my predictions now. So, yeah, here we go. Okay, so these are my ugly digits. So, for example, for the 0, I see the 10 probabilities, and you can see probability 0 is actually the highest. So good, this is actually a 0. For 1, actually that probability is the highest, so it is a 1. 2 is very good, so it should never be 1 or zeros. It's because I'm just using 4 decimals. So if you see 1, it means it's higher than 0.9999. Okay. 3 is great. 4 is okay. 5 is very good. 6 very good. 7 okay. 8 okay. Now we have a problem because this should really be the highest, right? But the highest is actually that one, which is the 4. So my model here is confused. It thinks this is a 4. So it is a very ugly 9, I'll give you that, but it's still a 9, it's not a 4. Okay? So that's a bit disappointing because we have a model that says 98.2 something accuracy, and I tried 10 samples and one of them is wrong. So okay, maybe I'm unlucky, but okay, that's too bad. Okay, so what could be a problem here? Because these are simple images, right? But what did I do to them? So I normalized them, but that's okay. But what did I do with the 2D thing? I flattened them, okay? So, well, that's not helping, right? If I give you a picture of a cat and a picture of a dog and I flatten them and I give you the 2 vectors, is it easy to recognize now? Well, unless it's a very flat dog, but probably not, right? So that's likely to be the issue here. The fact that I'm using this fully connected network where I have to flatten images because my input layer has to be flat. So how about we try that fancy LeNet thing, okay? Simple CNN invented by Lequin. So let's do this again. I'm going to train for 24 epochs, build the iterator, that's the exact same code. Here I'm going to build LeNet. It's a small variation over LeNet, but it's close enough. So I can see a first block, right? Convolution and pooling, right? Conv1, ReLU 1, pool 1. Okay, so first block of convolution to extract features and pooling to sample the image. Then another one, convolution, pooling, etc. Again, extracting features and again sampling again. And that takes me from the 28 by 28 image to, I think it's 4 by 4 or 5 by 5, I need to check. Okay, but much smaller. And this time I can flatten this and use a fully connected network, just like the one we saw before, to classify this. Okay, so it's really that LeNet that we saw this morning. 2 blocks, convolution, pooling, and then a very just one layer for classification. Okay. So of course, now you could say, well, why is the kernel 5 by 5, and why do I have 32 filters and not different number? And that's where you get into I would say the more experimental side of things, okay? And you could try training with 64 filters instead and see what happens, okay? But we can't go too deep today. And once again, training on GPU, binding, and initializing, and I'm going to use another optimizer called ADAM, which is a popular one these days. And I'm going to start with the learning rate of 0.1, but ADAM will actually change the learning rate as we go. Okay? Okay, so now let's train. And immediately we could see, well, I'm still on the same machine, still using a GPU, and this is way slower. Okay? The fully connected network was something like 0.7 seconds per epoch, and this is 2.4, so let's say 4 times slower. Okay, and if I run this on the GPU, it would probably be 45 seconds per epoch. So that's why the minute you move into, I would say, convolution, and the minute you start working with images, if you have a big data set, this is a very small one, so we could totally train it on CPU. But if you start having, hundreds of thousands, millions of images, complex network, this one has only 2 convolution operations. But again, state-of-the-art networks can have hundreds of convolution layers. So you can imagine that, of course, this is why you need those GPUs with thousands of cores to run all this stuff in parallel. So epoch 1 tells me 97.8 accuracy. Epoch 0 at the first epoch, which is even higher than what we got. So that's a good sign, right? That's a good sign. And let's go down, and we can see, okay, so of course we get to 1, and we get to validation accuracy of 99.1. So let's save this one here. Okay, and so 98.2 versus 99.1 doesn't feel like a huge difference, right? So of course we have to test once again. But keep in mind, this is a very different architecture. So I'm just going to load this one instead. And then I'm going to run my predictions again. And hopefully 0 is good. 1, 2, 3, 4. And I tend to get higher numbers because I only see 1 here, 6, 7, 8. All right, and this is where I look like an idiot half the time, because sometimes it doesn't work. And it worked. So I still look like an idiot generally, but not today. All right, good. So I get 93% accuracy on this 9 now. And so there's no doubt it's a 9. Okay? So as you can see now, we can be confident that this works a little better, right? This is a little more resistant to changes. Okay? And this is because, again, I'm not flattening, I'm just sticking to 2D images and extracting features and shrinking them as we go. All right. How much time do I have left? Okay, 10 minutes. So maybe we should try, okay, this one here. So of course, some of those models are insanely complex. So here we define them and train them ourselves, but most of the time you don't want to do that. Most of the time you want to take existing models that have been shown to work on a problem similar to yours, and you want to reuse them directly. You don't want to train those 100 or 200 layer models. It's going to take time. You need a lot of data to train them properly. It's not easy, and it's costly because you will need a bit of infrastructure to do it. So here I'm going to grab 3 models, which in their time won classification competitions, because there are such things, if you can believe that. And I'm gonna load those models, and I'm gonna predict the same image, and see what happens there. Okay. So let me clear this. So these models have been trained on a data set called ImageNet. Okay, and ImageNet is it's a huge image data set. It's got more than 1 million pictures with 1,000 categories. So people, no people, objects, animals, and plants. And I've got a file with the categories in there. So loading the model is exactly the same thing as we saw before. Okay, except this time I'm working with color images, so I'm going to predict 1 image with 3 channels, and these images are 224 by 224. This is how those models were trained. So I need to use the same size. Okay, I need to load the categories because I want those strings in memory to display the categories later on, the predictions. Again, I need to load the image with the OpenCV into an NT array. Prediction is the same, except I have 1,000 categories, right? So I don't want to display 1,000 categories. I just want to take the top 5 ones, let's say. So I'm just going to do that. I'm going to squeeze that vector, sort it, take the top 5, and return them. Okay? So now I can load my models. Okay, and I can run them. on the, here. I can run them on the CPU, see what happens there. Okay, so here's the image I'm using. And I can see, well, they all do a good job, right? The top probability for all three is a solid 80, 90+% for violin. I can still see a pretty big difference in prediction time. Okay, so VGG16 is the oldest one, ResNet is more recent, and Inception is even more recent. So you could see, you know, again, depending on your business problem, you could say, well, maybe this one has a slightly lower accuracy, but it's good enough, and it's 7 times faster than this one, so, you know, why not? Why not take that last one, just faster? Okay, or you could say, well, I don't care so much about saving half a microsecond, I just want the top accuracy, so I'll take the first one. Okay, but of course, you would have to test on a lot of images. Let's run this again on the GPU. And it will be interesting to compare. So 0.64, 0.34. Okay, so 0.64 is now 0.03, right? So you can see generally the GPU here for a single image prediction is maybe 20 times faster. Okay, 15 to 20 times faster. But does it matter to your app? That's the question, right? Maybe you're just happier with a less expensive CPU-based instance to run this. Right? Does it really matter to your app if you predict in 0.05 microsecond or 0.5 microsecond? Right? For this kind of thing, it probably doesn't matter a lot. So you just should probably stick to the CPU instance, which is going to be cheaper. Okay, so as you can see, this is how you use pre-trained models. Right? We didn't write a single line of code of deep learning code, right? We just loaded images and forwarded them, and we get state-of-the-art prediction with those, okay? But what if, and that will be the last thing for today, what if I need to use my own images, okay? So let's say you take one of those pre-trained models, but you want to classify, I don't know, let's take an easy example for Munich. You want to recognize BMWs from Mercedes, from Audi, from Volkswagen, right? Of course, ImageNet doesn't know how to do that, okay? The ImageNet dataset, I don't believe, it probably has cars and objects, and probably sports cars, etc. But I don't think it has brands, right? So you could say, okay, we're going to gather hundreds of thousands of images from those brands and build our data set, and we'll train on that. And that's going to work for sure, okay? That's going to work. But gathering those images, labeling them, et cetera, is a bit of work, okay? Especially the gathering part, right? Well, you could sit in the street and take pictures of cars all day long. Okay, that's going to get old, especially if you need 100,000 of them. You could buy that data, etc. There are many other ways. But my point is, it's time-consuming and probably expensive to build a very, very large data set to train from scratch. So what you could do is, you could say, well, these models, they don't know about BMWs versus Mercedes versus everything else. But surely they know about cars and vehicles. So some of that training is probably interesting to me, right? So could I take this existing network? Could I retrain it just a little bit on my specific images, in which case I probably do not need more than, let's say, a few thousands? And would I get good results? And the answer is yes. This is called fine-tuning, and it's the #1 technique that people use when they do deep learning, right? They don't go and train from scratch. They take a large model, train on a huge data set, and they fine-tune it on their own images. Right? Because it's a huge time saver when it comes to building the data set and, of course, training. So let me show you a quick example. Here, I'm going to use a data set called Cypher10. And, oh yeah, should have clicked here. So another popular image data set. And it's called Cypher10 because it's got 10 classes. Okay? So it's got, again, 50K images in 10 classes and 5,000 images per class. Okay? So let's say I have a pre-trained model. okay? And I have one here. So I trained ResNet 50, which is 50 layers deep, pretty big, efficient model. Took me a while to train it, on a GPU instance even, and I saved it, okay? And I did this some time ago already. Time flies. So I saved this model, and if I use my validation data set, I get something like 82% accuracy, okay? Which isn't fantastic. It's okay. This is a pretty difficult data set to learn because these are really small images, 32 by 32, right? And some of them are just impossible. So, for example, this is a cat. Is it? Yeah, exactly. It could be a fox. It could be a. Okay, it's not a frog, but it could be a dog. Seriously. And some of them are just impossible. The deer and the horse are pretty fun as well. So you could zoom in, and it's only 900 pixels. So at the end of the day, some of them are impossible to figure out, even for a human, I believe, which makes this data set interesting. So I train on this, but let's say now my business problem is to recognize cars and horses, right? That's all I care about. That's my $1 billion startup idea. Build a car and horse detector. Okay? Yeah, that's gonna work. That's gonna work for sure. I'm raising money right now, so if you want to jump in. So of course I could say, okay, let's take 1 million car pictures and let's take a 1 million horse pictures and fine, okay? Or let's take 1 million BMW pictures and 1 million Mercedes pictures, going back to my same example. But here again, I just care about automobiles and horses. So what I'm going to do is basically this. And this is using Keras. Keras is another open source library for deep learning. It's very interesting. I encourage you to read about it and use it. It's quite similar to MXNet when it comes to an abstraction level. And Keras can work with multiple backends. Okay, so Keras is actually an API sitting on top of TensorFlow, Theano, and hopefully very soon for Keras 2 on MXNet. Okay, it was available in Keras 1, and we're working on it for Keras 2 right now. So what I'm going to do, as you can see, and it's very readable code and very well commented code, of course. So I'm loading the pre-trained model, which is very similar to what we saw before. I'm going to freeze all the layers in this model. Okay, and I have to show you this part because this is how you do it. And this is why Python cannot be beaten, really. Okay, this is how you do it. They have a trainable attribute in Keras, and you just iterate over all the layers, and you set the trainable attribute to false, except the last one. So basically, I'm going to retrain the model only on the last layer. I'm going to keep all the previous weights for all the layers. Only the last one will be retrained. Okay, because I want to retrain for 2 classes and not 10. And of course, as you can imagine, it's easier to figure out 2 classes than 10. Okay? So this is what I'm doing, freezing the layers. And then I'm going to retrain, and you can read this code and figure out what it does. And I should start it now, because it takes a few minutes, because it's running on my machine. Yeah. Okay. No, bad idea. Okay, and I'm just going to train again using 5,000 cars and 5,000 horses. Okay, and I'm actually retraining with the same images that are already present in a training set. Okay, so I'm not even adding new data. I'm just saying now my output layer has 2 classes and just retrain on cars and horses. And I'm keeping all the previous training as well. Okay, so as you can see here, so here I'm just looking at what my baseline is, and it will be ready in 15 seconds. So this should say, so here I'm predicting with 1,000 cars and 1,000 horses, just to see what the starting point is for that pre-trained model. And it should say something like 88%. So that's my baseline. Okay, 88%, 0.8, okay. And now I'm just retraining again with 5,000 horses and 5,000 cars. And this takes a few minutes, so I'll go through the rest of the slides and we can see this result. Okay, so you get the point, right? I'm taking that pre-trained network, retraining it with 2 classes only, using very, very little data. So 88% is the baseline, and in 3 minutes, we'll see where we land. All right? Okay, so sorry? No, so I'm just retraining for the 2 classes. But before? Oh, before, yes. It was trained on that 10 classes, okay? Right? It was trained on those 10 classes. And again, the baseline accuracy for the 10 classes was 82%, I think. And the baseline for just for these 2 classes is 88. But let's see, by just retraining for a few minutes, how far I can get, okay? So again, all that stuff is on GitHub. So the links that I already shared this morning. If you want to start working with MXNet, so of course everything is on GitHub, you can. There's a separate repo for Gluon, okay? And remember the Gluon documentation that I shared this morning is a really, really good way to get started because it's a proper deep learning book. So it takes you through deep learning in general and then shows you how to get started with the algos. Okay, and the last thing I want to point out, and it's probably a good way to complement this session, is like this says, you know, the number one question I get after this talk is, okay, this is really great, but now how do I really get started? So I'm happy to answer this question again today, but I figured I could help a lot of people by explaining in a post how to do it. So I'm just basically sharing the resources in the right order, you know, how I learned this stuff. So everybody's starting point will be a bit different, of course. I did a lot of math back in the day, so maybe that was easier for me. But anyway, this is basically 10 steps with resources on getting on your way to deep learning. And people have run this, I've read this and followed those steps, and I get super cool emails telling me, yeah, this works, and I'm now learning this. So hopefully it will help you too, right? So this is how you can get started. Okay, so now the only thing that we're missing, of course, is the accuracy for this. Should have launched it. Okay, 110 seconds. Questions? You have 107 seconds for questions. Yeah.
You were training on now on 2 categories that were in the original model. Would this work if you were training on totally different categories?
That's a really good question. So the question is, would it work if I train on something completely different? If I trained on spaceships and, I don't know, satellites, let's say. And the answer is yes. And that's the magic of convolutional neural networks. Because as we do feature extraction, okay, in the early layers, we tend to extract very basic features, very basic shapes, like maybe lines and angles and diagonals. So shapes that will be present in everything, right? And then as you go deeper, and actually you will find some examples on the web of people are showing visualization of what those filters can actually detect. As you go deeper into the model, you see the filters detecting more complex shapes. And the deeper you go, the more complex they become. So that's why you tend to only retrain the very last layers, because you want to keep that early training. If I was training on something very, very weird, like, I don't know, apples and oranges, maybe, let's say, which are very different to the objects, maybe I could say, okay, I'm not just going to retrain the last layer, maybe I'm going to retrain the last 5 layers or the last 3 layers, and you know, to specialize those layers for those new shapes, okay? And that's part of the experimentation that you need to do. Okay, that's a really, really good question. Thank you for bringing it up. Okay, 5 seconds. Well, we can already see the result, can't we? Okay. So it's thinking for a while, but the answer is 98%. So, and this is running on my laptop, okay, which is why it's actually slow. But take this, okay? I took this complex model that I trained for hours and hours and hours, maybe days, if I remember correctly. I take even existing data. I'm not adding any new data to it. I'm just saying now, please relearn for one epoch on those few samples, and I can boost my accuracy from Yeah, it's up there. Oh no, it's here. From 88% to 98. So plus 10 points with 3-4 minutes of training. Okay, so like I'm saying, like I said, fine-tuning is really, really a weapon of mass destruction when it comes to deep learning. It's the fastest, most economical way to get really, really good results when you don't have a lot of data. Yeah.
Use that for retraining as well, that if you have real live data coming in.
Absolutely. Absolutely. Yeah, the question is, can you retrain it like that? So sure. You don't want to throw away your model. Okay, so maybe you have to experiment once again. It's very difficult to give you the solid. As you can see, all of this stuff is experimental, okay? So you could say maybe I'm retraining every day with incremental data, and maybe once a month I'm doing a full training. And you could even A/B test those things, right? You could say the incrementally trained model, does it perform better than the model that I trained from scratch all the time? Who knows, right? Who knows? You can figure it out. And that's a good transition to the next talk, because when you go into those discussions, you quickly get to, okay, how do I train at scale? How can I train 50 models in parallel? How can I deploy them? Blah, 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 blah. Okay, I would say the DevOps part of machine learning, which is really important. Okay, and that's the next talk. And I think you guys have a break, right? So thank you, because I probably don't. So thanks again for listening. So next session is SageMaker. So running more code, running more samples, but this time the focus will be on, I would say, the DevOps part of machine learning, and how do you scale that to a team of 50 people and without getting bogged down in infrastructure. Okay? So thanks again.